I'll be talking about few of the very basic things in biostatistics. My job has been made easy by the presenter before me or presenters before me. So I'll be talking about sample size and little bit about how do you calculate a sample size, what do you mean by a normal distribution, what is the role of standard deviation, skewness, z-score, some facts about central limit theorem and confidence interval. So it's a bit disjointed topic. One is not directly linked to the other, but in a way I will try to make it link to each other. And the focus will be for you guys to be able to write in the exam some important points about these things. All right. So sample size estimation, the first question is why we do it. So you can have a small sample study or a big sample study or a large sample study based on many factors. So the sample size as an investigator, you cannot determine a sample size. You have to pre-assess a sample size of a study based on many factors. But the understanding is if you take or you have a small sample size, then you'll not be able to detect the precise difference between study group and making the study more unethical. The results of the study cannot be generalized to a population. So it's a demerit to have a small sample size in a study. They can ask you why you don't take a small sample size because it will not be a representative of the population in general, or you don't have an external validity to the study as Tapas was talking about. Large sample size, you put more population to risk of the intervention and also making the study unethical. So both can be a problem. So suppose you're testing a drug which has a very significant side effect profile, and you don't need to test it in many individuals or even in humans. In those cases, a small number will be ethical practice. But for a drug that needs a very big data set to have some valid outcome of a study, in that case, you may require a bigger data set. So not that always, if you have a bigger sample size, your study will be good. It is not like that. It is based on many factors. If you unnecessarily make your study large or take a larger population of people enroll into a study, there is wastage of precious time and resources also if you don't need it. So overall, the sample size is an important factor that can very well determine whether the study will be approved or rejected by the medical community or medical fraternity. So it is an important part of any study. Now, components of a sample size calculation. So as I said, it depends on many factors. Predominantly, we look at 4 factors while calculating a sample size. So first of all, the significance value or p value or alpha value, the power of a study that we want, the effect size of the study that we estimate that this will be the effect size of the study, and the variability that has been observed. So these are the 4 parameters importantly come into play when you are calculating a sample size. There are other 2 factors also. If many people drop out of the study, then you have to preemptively enroll more people. So dropout rate, and also you look for event rate in the population. For example, you are testing a antihypertensive drug, okay? So you need to know what will be the estimated event rate. Event rate, I'll talk about it. Event rate in the sense how much blood pressure it can reduce in the population. Just an estimate before going into trialing the drug. So you have to have these parameters fixed before you enroll or before you start thinking about a study the first thing you do to calculate the sample size, you need to have these numbers or these parameters in your hand. Now we'll talk about one by one. I will not talk about the value per se or describe the value or what do you mean by p-value, but how it affects the sample size. That will be the important aspect of this presentation. So p-value represents the level of significance. We usually take a p-value of less than 0.05. That means the probability of difference in studying target due to a chance is only 5%, or there are 5% chances of detection in difference when actually there was no difference at all. So false positive results. This has been repeatedly talked about, so I'm not going in detail about this. This also is an indirect representation of the alpha error or the type 1 error that we know already about it. But important thing is the alpha error is inversely proportional to the sample size. When I show you the formula for the sample size calculation, it will be more obvious. Just remember that if your alpha error or other way around, if your sample size is less, your alpha error is more, and vice versa. If your sample size is large, then your alpha error is less. So this is an important component, p-value or the alpha error, in calculating the sample size. Now, second point, we talked about the power of the study. So type 2 error, as Tapas was saying, is the probability of failing to find the difference between two study groups when actually a difference exists, and it is known as the beta error or type 2 error, which represents the false negative result. By convention, maximum acceptable value of beta in a biostatistical literature is 0.2 or 20% chance that null hypothesis is falsely accepted. We talked about that in earlier lecture. The power of the study is then equal to 1 minus beta. Again, this is a repetition that in statistical analysis and in clinical trials, we try to keep our power more than 0.8 or 80%, right? So usually most clinical trials uses the power of 80%, which means that we are accepting that 1 in 5 times, like 20%, chances are there that we will miss a real difference. The power of a study increases as the chance committing a type 2 error decreases. That means your population number increases. So again, the power is more if you have a large population or large sample size. The third point, we talked about the effect size. So effect size is the minimal difference that the investigator wants to detect between the study group and is also termed as the minimal clinical relevant difference. For example, if you're testing two antihypertensive agent A and B, A reduces the systolic blood pressure by 20. We'll talk about that example later on. And B reduces the systolic blood pressure by 10. So the effect size is 20 minus 10 is 10. All right. It's very straightforward. The three methods that affects the or estimate the effect size. How do you do it? Before planning a randomized control trial, you can look to do a pilot study. Suppose you're testing a drug for the first time. You do the pilot study in your unit and another unit, which you know, and find out what is the gross effect size from that. Or you can look at previous studies that has been done on that drug or that intervention and find the effect size. For example, take any intervention in ICU. Suppose use of neuromuscular agent in ARDS. So you are planning to do a study, but how do you do? So first of all, you can do a study in your center only to see a pilot trial with 30, 40 or 50 patients to see what is the effect and what is the mortality outcome of that if you want to. Or you can look at other study from other continent or other country or any other researcher to see what was the effect size. And based on that, you take a number. So this is the effect size for that intervention. Or in very rare occasion, you can take an educated guess based on your clinical experience, which again doesn't have much of a validity. So effect size can be what you call extrapolated or can be measured by either a pilot trial or by previously reported data looking at it or by just an educated guess. Now, effect size example, suppose you're checking for a drug, which is the treatment with drug A results in reduction in the blood pressure, mean blood pressure by 10. And with drug B, the resultant drop is 20. So calculate the effect size. So effect size can be expressed as the absolute or a relative difference. So absolute effect size is 10. One is reducing by 20, the other one is reducing by 10. So that is 10. Absolute reduction or absolute effect size is 10 millimeter of mercury. Relative difference or reduction with the drug intervention is 10 by 20 or 50%. Obviously, this number 10 is 50% of 20. So 50% reduction. So this is a relative effect size is 50% or absolute effect size of 10 millimeter of mercury. So very easy fundamental about it. For continuous outcome variables, the effective size will be a numerical difference. For binary outcome, like effect of a drug on development of stress response, like yes or no. So if you have a continuous variable, then you will get a directly difference between the blood pressure from one person to the other person, or the mean blood pressure difference you get 20 minus 10 is 10. That is a continuous variable. But if it is a binary variable, you will have yes or no type of answer, which will be the effect size. Okay. For larger effect size, smaller sample size would be needed to prove the effect. But for smaller effect size, sample size should be large. So there is a problem in medical literature or medical what do you call a clinical trial. When we test something in a very large population, for example, if we start testing use of aspirin for preventing stroke or for preventing acute coronary syndrome. If you take 100 million patient or 10 million patient, then the effect will be very diluted. As the sample size increases, your effect size gets smaller and smaller because there are a lot of confounders, or not confounders, but there are a lot of other parameters that come into play, causing the effect size to be diluted and narrower and narrower. So there is a happy point, or there is a acceptable point when the effect size and the sample size both are at an acceptable level. If you increase the sample size, your effect size will be very, very less. In that case, there is no point testing that drug. If you say that I have tested aspirin in 2 million people and there is no difference between the result, yes, there will be no difference between the result because you have taken a very big sample, which is not required. So in that case, you have to be very cautious about what sort of number you need to have that desired effect size. So that's an important point in calculating the sample size. Effect size is determined by calculating the difference between the means divided by, I'll talk about that, by the pooled or average standard deviation from the two groups. Generally, the effect size of 0.8 or more is considered as a large effect and indicates that the means of the two groups are separated by at least 0.8 standard deviation. So we need at least a effect size of 0.8 between two groups. Effect size of 0.5 and 0.2 means moderate or small respectively and indicates that the means of the two groups are separated by only 0.5 or 0.2 standard deviation respectively. So if the effect size is less than 0.5, then the effect is not that great and the use of the drug or use of intervention may not be justified. So you need to have an acceptable effect size. Now, the next point that governs a sample size is the variability. So researchers anticipate the population variance of a given outcome variable, which is estimated by means of standard deviation. So there are many ways you look for or you estimate the variability in a sample, but standard deviation is the most important and most commonly used. Use of an estimate obtained by information in previous study because sometimes the variance may not be available because you're just starting the study. There is no population that you have identified. So where do you get the variance from? You can look for previous study. What was the variance there? Okay. For a homogeneous population, we need smaller sample size as variance or standard deviation will be less in this population. So we'll talk about if the population or the parameters are distributed normally in the population, in that case, a smaller variance is accepted and it's preferable because you know that the population is very homogeneous and the outcome will be homogeneous. In that case, your variance will be small. An example of variability. Let's take this example where we are looking at a diet program. Suppose we call that program as A on the weight of the patient. So we found that the weight ranges from 40 to 100. We're talking about the sample size, the starting of the trial. We haven't looked at the effect of the drug. Okay. So we are looking at a population which has a very wide variation of weight from 40 to 105 kilos, which is pretty big. So the standard deviation in this group will be bigger because the mean plus the standard deviation will be very big. Okay. Now we need to have a larger sample size to detect a difference between the intervention here in this case. Okay. It is a small sample, if a small sample size is taken in this case, the difference between the study group would be concealed by the inherent difference between them because of the standard deviation. Suppose because the weight range is varying from 40 to 105, and if the mean of that, suppose give a number to that, suppose the mean is 60 with a standard deviation of 15, like 60, so 60 plus 15 and 60 minus 15 is the standard deviation if you take. And if you find the effect of the drug A or the program A has reduced the weight by 5 kilos, which is less than the standard deviation, then it doesn't make any sense because the population is so varied. With that small number of people you have taken, you will not get a difference, which is statistically significant. So in that case, if you have a very inhomogeneous sample, then you have to increase your sample size to make it more normally distributed so that you will have a valid result. So these are the factors that determines your sample size. If you look at another example, suppose you have less variation of the weight, 60 to 80 kilo, you have 100 patients enrolled in that study, very less variation between the baseline characteristics and a small standard deviation. In that case, it is a more homogeneous group. So you can conduct the same study with a smaller sample size. You don't have to have a bigger sample size in this case. We talked about the dropout rate. Again, dropout rate are important. Estimate of number of subjects that can leave out the study or clinical trial. You cannot follow them up. So this is the dropout rate. And normally the size of the sample size calculation will have a number of study subjects required for achieving target statistical significance. Suppose you enroll 200 patients and out of that 150 will drop out. Then in that case, it will not work out. So you have to keep that in mind. What is the usual dropout rate? And you have to factor that into your calculation of sample size. Okay. Now, if n is the sample size required as per the formula, and if d is the dropout rate, then adjusted sample size, which is n1, is obtained by the following formula, where n1 is n divided by 1 minus d rate. So this is just for a statistical understanding. So you have to factor in the dropout rate while calculating the sample size. So basically, back to the second slide that I showed you, there are 4 major factors and 2 minor factors that that you have to look for while calculating the sample size. Event rate, we talked about that. It is usually the estimation from the previous literature, or you can do a pilot study and see. For example, if you're studying the association of smoking and brain tumor, the prevalence rate for brain tumor in the study population should be known prior to the study. You need to know that X number of patients had brain tumor in the population. You cannot start this study or sample size calculation without knowing the prevalence of brain tumor in the population. Sometimes we have to readjust the sample size after starting the trial because of unexpectedly low event rate in the population. Suppose you have started to see malignant hyperthermia in a population, and you need suppose the initial calculation or initial estimate effect size that you're looking at, which has given you a sample size of 300, but in your setup or in the participating centers, you'll not get that number very quickly. In that case, you have to rejig your sample size and readjust your sample size later in the study because of low rate of prevalence of the disease. All right, going to calculation of a sample size. What are the prerequisites? So it is a bit of a detailed statistical discussion. So the box on the right side is the sample size formula, where it 2 times Z alpha plus Z1 minus beta square times standard deviation square and the dropout square. The Z alpha and Z1 beta or 1 minus beta are constants set from this table based on what type of significance you want. Suppose you have an alpha error of 0.05 fixed in your study, then your Z alpha is 1.96. And if you fixed your beta error as 0.2, then your Z1 beta is 0.842. Factor these into this formula, get the standard deviation. Again, the standard deviation, you have to look for previous studies, what is their data, and or your pilot study, what is the data and what standard deviation you have taken from there, and the dropout rate. So these are all values that you have prior to starting the study to calculate the sample size. So Z alpha and Z1 beta comes from a table which is fixed based on what sort of beta error you are happy with and what sort of alpha error you are happy with. All right. Let's do a quick example. So you are planning to do a placebo-controlled randomized trial, assess drug A in preventing the stress response to laryngoscopy. So previous study, the average rise of blood pressure was 20 millimeter of mercury in systolic blood pressure during laryngoscopy with a standard deviation of 15. That you have gathered this information from a study or few studies. And now the question is, what should be the sample size to study the difference in mean systolic blood pressure between two groups with a significance of p less than 0.05 and a power of study of 90%. So you have kept not 80, 90%. So we want a significance of less than 0.05, power of 90%, and effect size of 20 millimeter of mercury with a standard deviation of 15. So these are the factors you know prior to starting the study, and you're going to calculate the sample size. So in this case, alpha is 0.05, 1 minus beta is 1 minus 0.2 is 0.8. Z alpha from the table that we saw earlier in this page, as you can see, Z alpha 0.05 is 1.96, and Z1 minus beta at 90% is 0.10, which is 1.28. So this is a constant that you take from this table and put it here. All right, so you have Z1 minus beta 0.842. So the sample size calculated to be 27.91. So you need to have 28 individual at least in each group to be recruited for this effect size with this intervention. Again, you have to factor in your dropout rate into that with that formula, if you have a dropout rate known from previous experience. So all those factors come into account to finally get a sample size. All right, so that was about sample size and calculation. Now let's talk about the standard deviation. Again, it is basic statistics. This can be a straightforward question in the exam. Standard deviation. So standard deviation, or the sigma, is a signal for the representation of that, is a measure of how dispersed the data in relation to the mean. So if you look at a distribution graph of the data, mean is population mean is represented at mu, and this sigma represents standard deviation. Similarly here, standard deviation. This diagram shows that your mean on the x-axis is both same. You can see mu and mu the same number, but the distribution of the data is different compared to both are normally distributed, but the peak of this curve is more compared to the other one, and the standard deviation is less in the figure down below compared to the one above it. We'll talk about that in the next few slides. So standard deviation can be small, can be big or large. So small standard deviation means that the data is clustered tightly around the mean. As you can see, the standard deviation is small, the intercept on the x-axis is small. So the data is more congested around the mean, making it a peak curve, right? But if the standard deviation is high, the data points are spreaded further away from the mean. As you can see, the data points are more distributed, and the curve is more flat compared to the one below. So in other words, if it is more spread out, means your standard deviation is high. More clustered around the mean means the standard deviation is low. Now this is the formula for standard deviation. I think If you want to remember a couple of formula in statistics, one of them is this one, because they can ask you about the standard deviation or calculate the standard deviation. So it's a summation of xi minus the population mean squared divided by n whole root over is the standard deviation formula. Xi represents individual data point, mu, as I said, population mean, n represents the total number of data points. Now, what is the role of standard deviation? Why do we need to calculate the standard deviation? First of all, it quantifies the variation. Suppose you have in the previous example where the weight varied from 45 to 90 kilo or 110 kilo, there's a very varied number of or quantitative distribution of the weight. Somebody is 40 kilo and the other one is 110 kilo. In that case, the data will be more widely distributed and the standard deviation will be more compared to if it is between 60 and 80. In that case, the data is narrowly distributed and you'll have a smaller standard deviation. So it quantifies the variation. The higher the standard deviation, the more distributed is the data. It identifies the outliers. Sometimes if you have a significant outlier, suppose you have a population of 20 people where 19 have a weight under 80 and the 20th person has a weight of 250 kilo. So in that case, your distribution will be different. Your standard deviation will be very different if you take a small sample from that data. Suppose out of that 20, you take another 10 out of them and then find out the mean of that and the standard deviation, which does not include that 210 kilo patient. In that case, your mean will be smaller, your standard deviation will be very small, and your distribution will be narrow. But if you take that 220 kilo patient into that separate 10 individuals that you take out from the sample, then it makes the mean higher with a bigger standard deviation. So if you find a normally distributed data, but you find that the standard deviation is high, then in that case, you should suspect that there are significant outliers. It compares data set again in that figure, the earlier one, the one we saw earlier, this one, it compares two data set. In this data set, it means that the standard deviation is smaller, the data is more homogeneously distributed and compact compared to this one more heterogeneous data, which is distributed in a wide variation. So it gives a comparative account of the data set. And also it summarizes the data. So usually the presentation of the data is usually mean plus standard deviation. So this is the conventional way we represent the data. So these are the main four important aspects of standard deviation or utility of standard deviation in clinical biostatistics. Now let's calculate the standard deviation, right? So we'll take 10 students, average height of 75 inches, and this is the data given there, and you are asked to calculate the standard deviation, right? You know the formula, this one. You don't have to remember at this moment, but we'll go step by step. All right, so first of all, the mean is 75, that is already been given. The mu is 75. You have one parameter already ticked off there. Now what you do, you have done this in probably in your 10th and 11th standard. This is a repetition of thing. So you subtract the mean from each data point. So xi minus mu, that is there in the formula. So you do it, you find those numbers first. Now you find the x, which is the difference between that. It will be spreaded around minus to plus based on where your mean lies. And then you square these results to make it a even or make it a positive number. And then the summation came as 784. And finally, x by n comes as 87.1 and square root of that is 9.3. In this case, the standard deviation is calculated to be 9.3. That means in one standard deviation, you take it 9, right? In one standard deviation, you have 75 plus or minus 9. In that case, was two standard deviation and 3 standard deviation. In 2 standard deviation, you have 95% of the whole population lie between that. So 75 plus or minus 18.6 is the range where 95% of the subjects will have their height. or if you take 3 standard deviation, 99%. So 3 times 9.3 is 27.9. So 75 plus or minus 27.9, you'll have all the people there. Most of the people will be the 99% of the subjects will be in that range. So 1 standard deviation, 2 standard deviation, and 3 standard deviation. We'll talk about that in the next slide. So 1 standard deviation that covers 68% of the whole population, which means 75 inches plus or minus 9.3 inches. 68% of the people will be in that range. 95% of the people will be 2 standard deviation, and 99.7% people will be 3 standard deviation from the mean. Now, sometimes they can ask you about what do you mean by standard error of mean. Suppose you have a population or a sample size of 500 or 5,000. Suppose you have a 5,000 sample size. It is very difficult to take or get the mean of the whole sample. Sometimes what we do is we divide the sample into subsamples, smaller samples, and get individual mean of that sample. And then those means are taken as individual data, and then from that we calculate the standard deviation of the mean. That represents your standard error of mean, right? It is an easier way to calculate how dispersed is the data, but it is not same as the standard deviation. So standard error of mean and standard deviation are wrongly used interchangeably in research, which is a wrong thing, is an error in representation of the data. Standard deviation indicates the dispersion of the data from the mean, the whole population data from the population mean. What is the dispersion is being represented by the standard deviation. But if you divide the whole population into 10, 12, or 15 or 100 smaller group, and then get mean of each that group, and then you plot the mean into a curve and calculate the standard deviation in that population, like standard deviation of the means of different group, then it is called as the standard error of mean. All right. So descriptive data should be precisely summarized with standard deviation. A reader or as readers are generally interested in knowing the variability within the sample and not proximity of the mean of the population mean. As I said, means of the mean. So you don't want that. Suppose I represented data in standard error of mean. So what it will say that I have divided the whole population into 20 groups. Each 20 group have their mean, like x1, x2, x3, x5 if you take the mean. And then I have plotted all the mean, and then I have calculated the standard deviation of the means. And if I say that this is your standard error of mean or SEM in this population, it doesn't make any sense. So you usually don't represent your means in terms of or mean of the means in terms of standard error of mean, because that doesn't make much sense. Rather than as a reader, you want what is the mean of the whole population and what is the standard deviation. That's how the representation should be done. Okay. But there are some utility of standard error of mean. So standard error of mean quantifies the uncertainty in estimation of mean. Suppose the population is very varied and a big population. In that case, standard deviation will not be an exact representation of the population, but it should be limited to compute the confidence interval measures and which measures the precision of the population estimate. So usually you don't represent the data in terms of standard error of mean. It is the standard deviation that you represent. It doesn't provide you a visual interpretation like the standard deviation, like you can see a bell-shaped curve and particular number is either 2 standard deviation or 1 standard deviation or 1.5 standard deviation from the mean. That means you know that this many people will have the same number. But if I plot the means of the whole population divided into 20-25 groups and then show you this is the standard deviation of each mean, it doesn't represent anything. It doesn't give you a visual impression. Now let's talk about normal distribution. This can be again another question. Normal distribution means, or the definition of normal distribution is also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean. So the mean will be in the center and the tails will be on either side. It shows that the data near the mean are more frequent in occurrence than the data far from the mean. As we can see here, suppose you're taking a performance score or SAT score of what 1600 some students, and look what is the score and what is the most common score, which is 1150. So, but the data is equally distributed around 1150. Almost same number of people are on the left and to the right. So this is a normal distribution curve or a bell-shaped curve that would have been described in the earlier presentation. Now, characteristics of a normal distribution curve: it is symmetrical. The left and right sides of the graph are mirror images of each other. It is bell-shaped. Most values cluster around the mean. Here, the mean is equal to median equal to mode. The tails of the curve extend indefinitely, though in this curve, you can see that they are meeting at the bottom, but they are described to be extend indefinitely. And the mean or the population mean you say as mu, and the standard deviation we talked about is sigma 1, 2, and 3 standard deviation. So whenever there is a question on normal distribution, you have to write down what do you mean by normal distribution? What are the parts of the normal distribution? Mean, median, mode, how they are. They are all equal. And possibly give an example. So you can see there are 3 data sets, the blue, green, and the purple one, where different number of patients are there and different SAT scores are represented. They have all normal distribution, but the mean value are different here. But because there are 3 different data set. At the same time, you have the same mean value. If you take another 3 sample, the first sample, the blue one, has a mean of 1000, the green has the same mean, and the purple has the same mean, but the distribution are different. We'll talk about that. What is this called as? So the mean can be same, but the distribution can be different. The distribution can be same and the mean can be different. That's what I meant to say in this case. But all of them are normal distribution curve because they are bell-shaped. Each half is mirror images of each other. So in this case, you can see the mean are different, but the standard deviation are more or less similar. In this case, the mean is same, but the standard deviation are different. So this can be different type of presentation of different data who will have a normal distribution and different type of values of mean and standard deviation. Now, what is the role? Significance. This is widely used in statistical analysis. People prefer to have their data normally distributed so that you can use easier test, as the previous speaker described about the test, whether normally distributed, non-normally distributed, that is a determining factor when you are using a statistical test. So you prefer your data to be normally distributed. It assumes the underlying normality in the parametric test. So you can use parametric tests, the specific test that is for normally distributed parametric data. It follows the central limit theorem, which sample means from a normal, which is valid for a normally distributed data. We'll talk about that limit theorem later on. And also it predicts the probability of occurrence of data point. Because you know what is the standard deviation, because the data is normally distributed. Suppose, for example, I give you the mean to be here as 100, and you have a standard deviation of this data as 10, and suppose your value is 80, then what do you mean by that? So you are between or at the 2 standard deviation from the mean, because 80 is 100 minus 2 standard deviation. So on the left side, you are in 2 standard deviation, where in this population group, you are here. All right. Suppose you have 50. In that case, you are beyond 3 standard deviation. So you are less than 1% in the population. So you will have a more confidence in telling about where you stand here if the data is normally distributed, if you know the mean and if you know the standard deviation. But if the data is not normally distributed, we'll talk about that. then you will not be able to say that where you lie in the whole distribution. Now, implications of standard normal distribution. You use any type of data. Suppose we are talking about weight of all the medical trainees in two countries or three countries. Suppose UK, US, and India, and the weight parameter are represented as pounds in UK kilograms, in US and kilograms in India. So they have different parameters, and apart from converting them, what is the other way of comparing them? So if the data is normally distributed, you can find a Z-score. I'll talk about that at the end of this presentation, which is a representative of the data of a particular person, whether it is represented as kilo or whether it is represented as a pound, because Z-score doesn't have a unit in it. So we calculate a Z-score based on a normal distribution curve and the standard deviation where the point lies, and then extrapolate that number to a score which is unitless. That is the Z-score. And then that can be a non-dimensional or dimensionless score in the analysis that can be used comparing with any data set, whether you take weight from India, whether you take weight from UK, whether you take weight from any other country which is using a different unit to calculate that or to measure the weight. So converts the data into a standardized table, that is a Z-score, and Z-score can be taken or can be measured from there, and then for the statistical analysis can be done. We talked about that. Compare different data set used to calculate probabilities and percentiles, and it forms the basis of hypothesis testing and confidence intervals. So when you say you are going to do this trial, which is being done in a smaller center, which has shown this mean normally distributed data with a 2 standard deviation of this much or standard deviation of this much. So all these parameter can go to calculate the sample size. So in that way, it helps if the data is normally distributed. Now, everything is not normal, and you will get data set or researcher encounter data set which are not normally distributed, and it is called as a skewed data. So skewness is a measure of asymmetry of the probability distribution of a random value or a variable. In a perfectly normal distribution, skewness is 0. So a normally distributed bell-shaped curve, the skewness is 0, indicating symmetry. Positive or negative skewness indicates a deviation from the symmetries. That means there are more outliers and the data is not uniformly distributed in the population. In that case, the distribution will be skewed and not a normal bell-shaped curve. In a normal distribution, as I said, the skewness is 0. Positive skew means the tail extends more to the right. In this case, the mean of the data is more than the median of the data is more than the mode. So mean, median, mode, it's more if it is a positively skewed data or a right skewed data. If it is negatively skewed, means the tail extends more to the left. In that case, the mean is less than the median is less than the mode, right? This is the usual convention that we look for. As you can see, this is a positively skewed or a right skewed data. This is a negatively skewed or a left skewed data, and this is no skew or a normal distribution curve. In a right skewed data, your mean is more than median is more than mode, and the reverse is true for a left skewed data. Now, measures of skewness. So visual, as you can see, this is a skewed data and this is a skewed data. You can see and tell based on the distribution, but it is not that easy always. In that case, there are other parameters that is used to measure the skewness. One is a Pearson's first coefficient of skewness, which is calculated by mode minus mean divided by standard deviation. I don't think you need to remember the formula for that, but at least you need to know that Pearson's first coefficient of skewness, there is a second coefficient also that measures the skewness, but you don't need to know about it. So first coefficient of skewness is the measure of skewness. So data is skewed to the right, has a positive skewness. Why we say positive? As you said, if it is positive, that means mean is more than median is more than mode. So if you put this formula, so mode minus mean, all right, divided by standard deviation. So where the mode is more than the mean, in this case, you'll get a positive number and the other way around. So data skewed to the right is called as positive skewed, and data skewed to the left is called as negative skewed. Based on where the mean is and what's the relationship between these two, it will be positive or a negative skewed. Implications. So statistical measures like mean, median, mode, and standard deviation is impacted by skewness because they are not equal, like a normally distributed waveform or normally distributed data. They are not equal if it is skewed, and affects the choice of statistical test. So if it is not normally distributed, as Srihari was telling, if the data is not parametric or not normally distributed, then the choice of test will be different. You have to do other tests for the data evaluation. Now, just going a little bit in summary and slightly in detail. So what you do, I'm not going to the table that Srihari told, but it is an abstract of that table. So you have to see what data type it is, whether it is normally distributed, not normally distributed. If it is normally distributed, the skewness is 0. That is mean, median, and mode are same. So you do parametric test. We talked about that. Srihari has told. If it is positively skewed data where the mean is more than median, then or it is negatively skewed. Once you have a skewed data, then you go for non-parametric test or test for non-parametric data, right? There are different types. We talked about U-test, Wilcox sign test, or Kruskal-Wallis test, based on whether it is paired, unpaired, and all those things. But if it is normally distributed, you do the usual test. If it is skewed, then you do these other tests. If there are more outliers, then again, one of these non-parametric tests has to be used. So basically, the steps that needs to be done, first, how is the distribution of the data? Is it normally distributed? Then these are the tests, paired, unpaired, based on the data set. If it is not normally distributed, positively skewed, negatively skewed, then other test has to be considered. Now, something called as a kurtosis. So we talked about this waveform earlier. The same mean, but the distribution of the data is different. Okay. The normally distributed normal data is called as mesocutic, right? The middle one, which looks like a normally distributed curve. But if the data is very narrow with a lower standard of distribution, then you get a leptocutic wave, which is this one, that picked one, where you have the same mean, but the standard deviation are less. And platycutic curve is where you have the same mean again, but the distribution is very wide with a longer tail. So that represents the height, represents the kurtosis, as called as kurtosis. Now, why we need a kurtosis or assess the kurtosis? Using the wrong statistical test can lead to incorrect conclusion. For example, parametric test on a heavily skewed data. Again, heavily skewed data may produce bias estimate and false positives. So if it is a not normally distributed skewed data, then in that case you have to check different tests or take different tests in that case. And again, non-parametric tests sacrifice some power but are safer to do in non-normal distribution. So we talked about that. Skewness number, if it is more than 0.5, then you look for other test or non-parametric test. Okay. And if the skewness is more than 0.5, you look for normality. You plot the curve and see whether it is normally distributed or not. Sometimes there is another way of making the data normal. If they are not normally distributed, then we do a logarithmic derivation of the data, or log rank we do. In that case, we plot the logarithmic value of the data to make the distribution more normal. And in that case, we can use the parametric test instead of not using them. All right. Now, Z-score, this can be again another short note for you. So Z-score is also called as a standard score, gives you an idea how far from the mean a data point is or how many standard deviation below or above the population mean a raw score is. Z-score are a way of compare results to a normal population. To be more precise, suppose you have Mr. X who has secured 190 marks in a test and the mean mark of the population is 150 with a standard deviation of 25. Then how will you compare his mark to the average person mark, right? That is the Z-score that you have to calculate. Assuming a normal distribution, the Z-score formula is X minus mu by sigma, where you need a standard deviation, population mean, and the data. Now, your Z-score is 1.6. That means your number of 190 is 1.6 standard deviation onto the right side of your mean. So you are doing pretty well and you are on the right side of the curve. Your standard deviation is 1.6 from the mean. So that's where the Z comes in. It is a it doesn't have a unit in it. So you can retrospectively look at a Z score to compare data which units are not comparable. You can compare inches with centimeters, you can compare inches with yards or everything. If you have a Z score calculated, and then you can compare all this data in different units together. All right. Usefulness of Z score again, probability estimation. For example, if you have one standard deviation where the Z score is 1, there is 68% chance of randomly selecting a score between -1 to 1 standard deviation from the mean. As you can see, this is the first line. This is the Z score of 1. Sorry. How it is used, Z score again, the same thing. I'm going around in circle. The utility of Z score is same as the utility of normal distribution curve, but you have to word it a little bit different. So hypothesis testing. So using a Z score table, it lets us to quickly determine the probability associated with a specific value in the data set. Suppose a data has a Z score of 1.8 plus 1.8. That means it is nearing to 2 standard deviation of a normally distribution curve. That means about 90% of the chance, there's a 90% chance, or in the whole population, whatever you have secured as a mark or whatever is your weight is within the 90% population of the whole 90% people of the population. That's the Z score. Calculate the Z score for a particular value. So there are steps to that. So you always refer to a Z score table, which is readily available. You have a data, you have a standard deviation, put those two like going on x-axis and y-axis and find the Z score from that. This will provide you an idea about the probability of having the result by chance also, like p-value. And with that Z score, you can look at the p-value table. What is the p-value associated with it? So suppose you have, just giving a random example, you are looking at your weight is 54 kilo in a data set of 1,000 people with a standard deviation and mean you have. And in that case, you calculate your Z score, and based on that Z score, then you go for a probability. On the same table, you can trace down and see what is the probability or significance of that, right? You can get a p-value in that. It helps to compare data set which are different from each other. As I talked about, they can have different scales or unit, but Z is not unit based. It is just a number. So you can compare two different data set with two different units. It also can outlie or identify outliers. If the Z score is more than 3 or less than 3, that means they are lying after 3 standard deviation, which is less than 1% of the population. Now, next point, we'll talk about central limit theorem. It can be a short note. It's very simple, basic understanding actually. You can have different type of distribution if you take smaller population group. Suppose we are talking about the population of Delhi, and you take each suburb of Delhi, like whether it is whichever, like you take Rajendra Nagar or somewhere, etc. You plot each of them, they will have a different distribution. But the central limit theorem says that the sampling distribution of a sample mean approaches a normal distribution as the sample size increases, that we have talked about. But if you combine all the suburb of Delhi together, then the distribution will be more normal distribution. That's what is central limit theorem, regardless of the shape of the population distribution. So individual will be different, but if you combine all of them, the data more or less reaches to a normal distribution. This holds true if the sample are independent and identically distributed. So that means that's the gist of the central limit theorem. Basically, if you increase your sample size, your data tend to be normally distributed. Now, explanation of central limit theorem. So take multiple random samples of a given size from any population distribution. Compute the sample means for each sample. We talked about Z value that we are talking about. As the number of sample increases, the distribution of these sample means becomes approximately normal. Suppose you have 100, a sample of 100, and you have divided into 10 each. So you have 10 groups. You calculate the means of each group and plot the distribution. It may not be normal distribution. It may be skewed to one to the other. But if you increase your sample size from 100 to 1000 and divide them into suppose 300 or 400 equal groups or any groups, 400 groups, and then start to plot these means, then the distribution becomes more normal or more normally distributed bell-shaped curve. So this is called as central limit theorem. The mean of sampling distribution equals the population mean. So what happens is if you have a bigger number of bigger number of population, and you take small samples out of it. If the population is big, then your sample mean tends to reach the population mean. Both the numbers are more or less similar, which you can say in 100 people, you have 10 sample mean, which can be differently distributed, and the distribution is not normally distributed. But if you take 10,000 people with 100 groups, each group having 100 people in that, then each individual mean of each group will be more or less similar to the population mean. Suppose the whole 1,000 people had a mean of 5, and each individual group of 100 will have a mean of 4.8, 4.9, 5.2, like that. But if your population is smaller, 100, and if you have divided that 100 into 10 groups of 10 each, but the population mean in that 100 is 5, individual sample will have a mean of 2, somebody will have a mean of 8, somebody will have some group will have a mean of 7. In that, average will be whatever 5, but the distribution will be normal. It will be more skewed to one side, but the mean will be maybe the same, but individual means will be different to each other. All right. Importance of central limit again forms the foundation of inferential statistics. Inferential statistics is the concept that we say a hypothesis has to be tested in a valid number of population to make the observation valid. Suppose you cannot do a intervention trial in 10 people when the occurrence of the disease or occurrence of the effect is more common. Suppose you're testing an antihypertensive drug where 50% of the population are hypertensive. You cannot test the drug in 10 patients. You have to have a bigger sample, right? And on the other hand, if you have a rare occurrence of a disease, in that case, it may not be valid. This argument may not be valid. So that's what is inferential statistics. You have to have a good number of sample size to have some have some valid results from a trial. Enables the use of parametric test even if the population is not normal. So what happens is if you increase the population size, then your normal non-normal distribution becomes normal, or you can convert those numbers into Z score and make it plot, which can be a normal curve, and then you can use a parametric test for those normally distributed data. So initially the data was not normally distributed, but you converted them to either you take the log score of them or put the Z score on them and get the data more normally distributed, and then subject that data to a parametric test. So you can convert them to a normal distribution curve. Provides the basis for confidence interval and hypothesis testing. That's self-explanatory, and facilitates the estimation of probabilities of sample statistics. Now, last thing that I will be talking about is confidence interval. So confidence intervals, as you know, is the mean of your estimate plus or minus the variation in that estimate. It will be obvious when I go to the next slide. So before understanding a confidence interval, you need to know what do you mean by confidence level. So 1 minus alpha is the confidence level, 1 minus beta is the power. Now, so if you use an alpha value of 0.05 less to be statistically significant, then your confidence level is 95% in case of detecting a true result. If your p-value or alpha value is 0.01, then your confidence level is 99%. So as your alpha value goes up, your confidence level comes down and vice versa. Now, why do we use a confidence interval? So you can calculate confidence interval for many kinds of statistical estimates, including proportion. Proportions are represented as a value plus confidence interval. Population means are represented as value from confidence interval. Difference between population mean and proportions, if they are there, then they can be represented as a number plus or minus confidence interval. And estimates of variation among the groups. You are talking about two groups or comparing about two groups, then you can represent the data, whether it is a proportion, whether it is a mean, in terms of mean and confidence interval for both of them. Now, example, you survey 100 Britishers and 100 Americans about their television watching habit. Both groups watch average of 35 hours of television per week. So the mean for both the population is same, but they are not same. How? If you look at this distribution, the green are the Britishers and the blue are the US people. They are more narrowly distributed around the mean. We talked about this. This kurtosis is high for the blue group. So US people watch a more or less similar number of hours compared to the British people who watch very variedly. So the British people surveyed had a wide variation in the number of hours watched, while the Americans are watching similar number of hours to each other. Now, even though both groups have the same point estimate, which is the mean, average number of hours watched is 35 hours, the British people estimate will have a wider confidence interval than the American estimate because there is more variation of the data. So the confidence interval will be wider for the British people compared to the confidence interval of the American people. Again, that represents the homogeneity of the data. If the confidence interval is more, the data is more inhomogeneous. If the confidence data is less, then the data is more homogeneous, inversely related to each other. The formula for confidence interval is based on the population mean, which is X, Z score, the critical value of Z distribution that can be calculated, or you can get it from the table. Sigma, you have to calculate the standard deviation of the trial and number of patients or number of subjects in the trial. So for calculating the confidence interval, you need to have the Z score and the population mean. These are the two things you need to have with the standard deviation. Utility, where it is used. So quantify uncertainty, provides the range rather than a single point estimate, highlighting the precision of the estimate. So it tells about how precisely your value is correct. Suppose you have a value which is X plus a narrow confidence interval. That means the value is more representative of the population and it is uniformly distributed. If you have a wide confidence interval, then the data variation is varied, and the precision of that point estimate is not that good. For example, if you have a calculated weight, suppose we found out that a drug reduces the weight by 8 kilo, or A and B, there are two drugs used to reduce the weight, and A reduces the weight by 8 kilos, but with a confidence interval which is very wide, compared to B, which is also reducing 8 kilos with a narrow confidence interval. That means the B drug is more reliable compared to the A drug based on this finding. The precision of that number, 8 kilo, is more appealing for drug B compared to drug A. Compare the groups. It helps to assess if two groups are statistically different. Overlapping confidence intervals suggest that there is no significant difference between the groups. If the confidence interval of both the groups are overlapping to each other, then there is probably no statistical significance between the effect of the intervention of the drug between the two groups. Decision making, widely used in clinical trials, epidemiology, and public health. This is the way you represent the data with the confidence interval. And transparency reflects the validity in the data and reliability of the result. If you have representation of the confidence interval which are overlapping to each other, then your data probably is not valid, or your effect is not valid, compared to if your confidence interval are wide and non-overlapping. That means your effect is more pronounced and more effective, or significant. That was my last slide. Thank you for your patient listening. If you have any other questions, you can post or ask me.